So this is example number 5. You need to find the coordinate of the inflection point, and then you need to show the intervals in which the concavity changes through that inflection point. So firstly, we are given with a function y. Since this topic belongs to the application of differentiation, definitely we are going to use differentiation in all of our examples and exercises. So differentiate this one once to get your first derivative. This is simply a quotient rule. For the first part, you will have ln x minus 1 divided by ln x and square. Okay, so we are not letting this one equals to 0 because we are not finding the turning point, but instead differentiate it once more to get our second derivative. So for this part, it's a little bit tedious. I'm going to show how I get to the simplified version. You're going to have ln x squared minus ln x minus 1 multiply with 2 ln x. This one is a v, which is the ln x square multiply with differentiating of u, so you get, it should be 1 over x over here. So let's put it this side. Okay, so this one will have 1 over x with it. This second part, this one is a u, and then we're going to differentiate our v, and this will be a 2, and then ln x, and then differentiating whatever inside, you will have 1 over x. So since the first term have 1 over x, the second term also have 1 over x, I might as well put them together like this, and we're going to see that the v is going to be squared, hence we get to the power 4. So if you multiply the 2 ln x with this one and then with another one, you will get a very lengthy expression, but you can factorize ln x outside, and then it can be cancelled with one of these ln x in the denominator, leaving you only with 2 minus ln x with an x and ln x cubed for the denominator. Okay, so again, like what we have mentioned before, we are not worried with the complicatedness of this denominator, because by letting the d2y dx2 equals to 0, then denominator will be multiply with 0 and equals to 0. So we are looking at the numerator itself. If the numerator is complicated, then we are worried. Okay, so finding, this is the new stuff, finding inflection point. We are going to let d2y dx2 equals to 0, then you simply have 2 minus ln x equals to 0, and this is very simple to see that your x is going to be E2. So the E2 you can calculate from your calculator, which is about 7 point, I think it's 8 something, but you can clarify it later. Okay, but what I do know is going to be 7 point something. Okay, and that is important for later part. Now that we have our x, so when our x is equal to E2, then your y is E2 divided by ln E2, and this one can be simplified as E2 over 2. Now you can use decimal points to write this coordinate, but by using the E, we can have an exact value for this one. So our inflection point is E2, E2 over 2. So that is the first part, which is finding the coordinate of the inflection point. Now to show the interval of concave upwards and downwards, or vice versa, so we're going to draw our table of concavity. It's almost the same as our table of shape of tangent as what has been said in the summarization part. Okay, again you have your x. I know that it's going to be E2 over here, and then it's a 7 point, yes, something. Let's write it using this blue color. It's a 7 point, can be anything, but knowing that it's a number in between 7, so I can use 7 over here and 8 over here, and this 7 and 8 should not be making this function undefined, whether it's y or d2y dx2. So it's really safe to be used over here. And for this part, yes, I'm going to use the d2y dx2 notation, so that you will not be confused. Okay, so you can write concavity or you can write concave, and this one will yield 0, meaning it's a dash over here. This is a dash, okay, and as of 7, it will give you a positive, a very small number, 0.001 or along that line. And if it's a plus, then it's an upward, concave upwards, and this one will give you a negative, very small number, so it's a concave downwards. So that is the interval of whether the function is concave up or downwards, depending on the function itself. And that's for the second part of this example. So only for this particular exercise, we will not have the same or similar duplicate question, because we would like to, because this one is pretty repetitive, and then it's pretty much self-explanatory for other examples. So for the exercise number 5, we are going to do a little bit of different situation, but related to our second derivative test.